from the new set to validate the robustness of the model. Here we have some results. This is just a raw spectra of what it looks like for the spectral acquisition of the biomass. There's a lot of information here, which we don't need all of them, so we just focused on spectroscopy from 800 to 1800. And these peaks are corresponding to certain chemical bonds. These bonds, then through the literature, we were able to assign these bonds to the certain chemical components inside the biomass. You can see it can be a cellulose, hemicellulose, lignin, or extractives and lignin. Then the next step, we use the absorbance values of each peak. The position of this absorbance values is like a chemical signature of the molecule. And the intensity of these absorbance values give you a rough idea about how much this component you have inside the sample. And also we use the chemical composition data from the wet analysis to train the model. Then we fed this data as an input data for our modeling. We use just an Origin Pro as a software, and then we tried to find the meaningful relation between these two data sets to correlate them. We use different regression models like principal component regression, multiple linear regression, but none of them gave the meaningful result for us. Then we found out that partial least square regression model were able to handle the collinearity and multidimensionality between these two data sets. Then to check the robustness of the model, we tried out new samples and tried out to determine their composition from just the spectroscopy. Here we have cellulose, lignin, and extractives. On the y-axis, we have actual amounts, and on x-axis, we have predicted amounts. As you can see, we can have a kind of linear relationship which we were looking for. Of course, there are some small error of margin, but when you look at the scale, it's so small. It's from, like, for the cellulose, it's just from 40 to 44%, so it's a small error, I would say. And then the next Sumaya will continue.